Hello everyone. In this session, we'll discuss mean value theorem. These theorems are based on intermediate value theorem. So, we'll start with the first one, which is Rolle's theorem. Let's say there is a function f of x. For a function f of x continuous in the closed interval a b, differentiable in the open interval a b, and also f of a is equal to f of b, then there lies at least one point, I'm writing it as C, such that C lies between A and B. So there lies at least one point C for which f dash of C is equal to 0. Right? So for a function f of x, the function needs to be continuous in the closed interval, differentiable in the open interval, and the function value at the endpoints a and b are equal. Then there lies at least one point. So there can be more than one point also, for which and this point lies between this range a and b. So there lies at least one point c for which the derivative at that point is equal to 0. So this is Rolle's theorem. Next is Lagrange's mean value theorem. In some of the case you may find mean value theorem written as MVT. So in this case, let's say again there is a function for a function f of x if it is continuous in the closed interval a b and differentiable in a comma b, that is open interval, then there lies at least one point, let's say C, where C lies between A and B, such that f dash of C is given as f of B minus f of A divided by B minus A. Right? So the only difference between Rolle's theorem and Lagrange's mean value theorem is that the function may not be equal at A and B, but again there is at least one point. So there can be more than one point C where C is between A and B, such that the derivative at that point is f of B minus f of A, divided by b minus a. So if we try to understand the graphical sense of this, this is nothing but, let's say we have a function and it is continuous and differentiable. So this function is continuous without any bend or without any break, or there is no slope which has infinity tangent and like that. Graphically we can say this is continuous and differentiable between a and b. Then if we join this line between a and b, it may have a slope like this. Let's say this is f of x. Then this Lagrange's mean value theorem means that there is at least one point for which the slope is going to be, let's say at this point, the slope is going to be parallel to this line joining f of a and f of b. This is f of a and this is f of b, right? And there are also possibility then we can have more than one point. So what if this function is like this? Then we can have this line parallel to this line joining a and b like more than once, right? And also Rolle's theorem, which had an extra condition that f of a is equal to f of b, is like we are going to have, so it is a special case of, let's say this is a, this is b, or we can take some other point also. Let's say this is b, this is a. Then f of a and b are same. Of course this is continuous and differentiable in this region. So there will be a point c for which the function's derivative or the slope we are going to get is going to be parallel to the x-axis. Why? Because f of a and f of b are equal, so f of b minus f of a will become 0. So Rolle's theorem is a special case from Lagrange's mean value theorem, right? Also, although we may not come across questions on this, but there is also one more mean value theorem, Cauchy's generalized mean value theorem. I'm not going in detail, but I'm just writing the expression that f of b minus f of a divided by g of b minus g of a will be f dash of c divided by g dash of c. We are expecting that gb is not equal to ga and f dash of c and g dash of c are not 0 together. Rest is same, like the function is defined and it is continuous between a and b, closed interval. It is differentiable in open interval a and b. Then we can say that f of b minus f of a divided by g of b minus g of a can be also given as f dash of c divided by g dash of c. Obviously this c is lying between a and b, right? So you may not get questions on this, but a rough and a short knowledge on this is provided.